Hey guys, today we're going to talk about continuity and discontinuity within a function. First of all, what does that mean? A function is discontinuous if you need to lift your pencil in order to draw the graph. So I've got three examples here of discontinuity. You can see two of them here. There's a third one that I'll show you in just a minute. These are three different types of discontinuity. This first one is called infinite discontinuity. Infinite discontinuity. From both sides, you can see this graph approach the y-axis, x equals 0, and it gets infinitely close, but even as these go up infinitely, they're still never going to touch x equals 0, even though they'll get infinitely close to each other. The next one is called jump discontinuity. I'm just going to abbreviate discontinuity. As you trace this graph, it's approaching x equals 0, and that's open right there, so it never actually reaches it here. But it does touch x equals 0 up here. On this side, it gets infinitely close to x equals 0. Here, it touches x equals 0 and then goes off to the right. That is called jump discontinuity. You trace down here and then jump up to here. The third type of discontinuity is called point discontinuity. This graph approaches x equals -2 from both sides, and it's just that one point that it skips, so it's discontinuous at x equals -2. So this one's discontinuous at x equals -2 because it never touches that one point. This one's discontinuous at x equals 0. Even though it does touch that point, there's a gap here. And this one is discontinuous at x equals 0 because it never touches x equals 0. So the continuity test, to determine if a function is continuous at x equals c, the first thing you have to check for is, does f of c exist? A function is continuous first of all, if f of c exists. In our first graph up here, f of 0 does not exist. It fails that test. In our second graph, f of 0 does exist, so it actually passes the first test. In our third graph, f of -2 does not exist, so it's discontinuous there. Fails the first test. The second part of the continuity test is that the function approaches f of c from the left and the right, and it does that at the same y value. I'm going to zoom out a little bit so we can see all three graphs at the same time. So the first graph, f of 0 doesn't exist. It failed the first test. It actually passes the second test because from the right side, it's approaching f of 0. From the left side it approaches f of 0. From the right side it also approaches f of 0 at the same y values. So it passes the second test, but since it failed the first test, it is not a continuous function. If it passes both tests, it's continuous. This one failed one of them, so it is discontinuous. This one passed the first test because f of 0 exists, but as it approaches 0, it does so at different y values. So it fails the second test. So it is not continuous. The third one failed the first test because f of -2 does not exist. It does pass the second test because it approaches from both sides at the same y value. But all three of them failed one test, so they are discontinuous functions. Next, we're going to test a function for continuity at a particular x value. So we're going to check, is this continuous at x equals 2? I've got the calculator here for this reason. On our calculator, in y equals, put in 8 over x, and go to the graph. And that's what our graph looks like. So I'm going to draw a rough sketch of that graph. Looks about like that. What I'm concerned with is the x value of x equals 2. And x equals 2, is this continuous? The first thing we need to find out is whether or not f of 2 exists. So what I'm going to do is trace 2, enter, and I get an output of 4, so that tells me f of 2 exists. So when x is 2, y is 4, that x value actually exists on the graph. It passed the first test of continuity. The second test is whether or not the graph actually approaches that particular point from the left and the right at the same y value. I see it approaching here from the left, here from the right at the same y value. So I would say this function approaches f of 2 from the left and the right. And it does so at the same y value, so this is continuous at x equals 2. Clearly, you're going to have to lift your pencil as you trace this function. So as a whole, this is not a continuous function. But at this particular point, it is a continuous function. So it's not a continuous function, but at x equals 2, it is continuous there. The next example, we need to graph y equals the square root of x minus 5 and check for continuity at the x value x equals 5. So y equals, and we'll clear out what's there. We want the square root of x minus 5. And graph. Okay, so that's what our graph looks like. I'll draw a rough sketch of it over here. X-intercept is 5, and it looks about like that. So if I trace the x value of 5, I get an output of 0. That's a real number, so f of 5 exists. It passes the first test. The second test is whether or not the function approaches from the left and the right at the same y value, and I only see this function approaching from the right. So it does not approach f of 5 from the left side. So our first graph over here, we can say this one is continuous at x equals 2 because it passed both tests. But this graph over here, we would have to say is not continuous at x equals 5 because it failed the second test. We'll end today with a little bit of practice on some algebra skills. So we are going to solve equations with multiple variables for just one particular variable. So we are going to solve this equation for y. Okay, so the first step I would do is move this 9 to the other side. So it's going to become x minus 9 equals y over 11. Then I need to multiply both sides by 11 to get y by itself. So I have 11x minus 99. Okay, number 2, I'm going to show two different ways here. So I've got 10 over y minus 7, and what I can do is multiply both sides by y minus 7. So I get x times y minus 7 equals 10, and then divide both sides by x, and I get y minus 7 equals 10 over x. And then I can add 7 to both sides, so y equals 10 over x plus 7. Okay, now a shorter way to accomplish getting this y minus 7 over here and the x down here, I can think of this as a proportion, and one property of proportions is that I can always swap things diagonally. So I can just swap those. Y minus 7 and x just change positions. Okay, we can always swap diagonally. And then add 7, y equals 10 over x minus or plus 7. Okay, so both of these ways are effective. This way right here is more efficient. So number 3, now I have an x, y, and z. I'm still solving for y. So first I need to get this and this over to the other side. So I've got x minus 10 z plus 12 equals y over 4. Then multiply both sides by 4, and I get 4x minus 40z plus 48 equals y. And number 4, I'm going to do similarly to number 2, where I swapped diagonally, but first I have this 2, this minus 2 that's blocking me from doing that swap, so I will add that to both sides. So I get x plus 4 equals 2z over y minus 7. Now I can swap diagonally, so I can switch this and this diagonally. So I get y minus 7 equals 2z over x plus 4. And then I can add that 7. Y equals 2z over x plus 4 plus 7.